The teacher should predict where the first fundamental frequency is to make sure you get near it when you're adjusting the sine wave generator. So let's take an example how you do that. Let's have the length of a tube being 132 centimeters. Predict the frequency of the fundamental harmonic of the open tube, part 1 of the lab. That means n is equal to 1, and we're taking the speed of sound as 340 meters per second. So let's solve for f sub 1 open, fundamental frequency of an open tube. We plug in the numbers, and note we use meters for the length of the tube, and we get about 129 hertz. Now the lab called for taking half the length of the open tube for the closed tube. So we're going to do that. We'll take half the length, which is 0.66 meters, and then try and find where the fundamental frequency for the closed tube is. Slightly different equation. Right here we had NV over 2L, now we have NV over 4L, but we cut the length in half. And look at this, we get the same fundamental frequency. The purpose of part 1, or trial 1 of this lab with the open tube, was to calculate the speed of sound. So in this case, we have a tube of 132 centimeters, and we found the first resonating frequency by ear at 136 hertz. So calculate the speed of sound. So here's our data table. Here's our frequency, and you have speed of sound here. So rearrange that. So the velocity, the speed of sound, is 2L times F over N. N is equal to 1 because that's the first loud sound we heard, the first resonating frequency. And we calculate the speed of sound at 359 meters per second. We now move on to part 2. And this time we cut the length of the tube in half, and we use the speed of sound velocity that we found in part 1. And this time the length of our tube is 0.66 meters, and we find the first resonating frequency we calculated by n times v, and here's the velocity of the speed of sound from part 1, and we find that the resonating frequency is 136 hertz. Why is the fundamental frequency the same for the closed tube as the open tube? The length of the closed tube was set to be half that of the open tube. The constant in the denominator of the closed tube's frequency equation is twice that of the open tube, so that cancels out the length difference, resulting in the same frequency. You can set the length to any value if you'd like the result to be a different frequency. And the final part of trial 2, part 2 for the closed tube. Find the fundamental frequency experimentally by listening for the first resonance. Suppose you heard it at 131 hertz. Right, this is what you heard. This is what you calculated using the data from part 1. We can now use the percent error formula to calculate the difference in the calculated fundamental frequency and the fundamental frequency heard. This is really not proper, as both values rely on calculations and not pure measurements. The correct way is to use percent difference, which will be shown after this calculation. Percent difference as opposed to percent error. For percent error, we're going to do calculated value minus the value from demonstration divided by value from demonstration. Typically, this term is a generally accepted value that people have researched and done many experiments on. And we haven't done that in this case. That's why this isn't really the right way to do it. But we'll go ahead and continue this, and the next slide will show what should be done. Percent error comes out to be 3.82%. Oftentimes when students do this, they find about 10% error. Please keep in mind that there are variations in where each person or group hears the loudest resonance in addition to the errors previously discussed. Percent difference is used when neither value is a generally accepted value. An example of a generally accepted value is the charge on an electron. It has been measured over and over and is accepted by the scientific community. In this lab, neither the calculated nor the demonstration values are generally accepted. So here's what we do for percent difference. We take the difference between the two values that we measured and calculated, divide them by their average. So we're finding the percent difference from an average of the two values. Take the absolute value, multiply it by 100%, and here's how we find the average. It's value 1 minus value 2 over 2. And then the 2 comes up because you don't want to have two horizontal lines here. So your percent difference is twice the difference of your two values divided by the sum of the two values times 100%. Let's compare the percent difference in this lab to the percent error. Because the two values of the fundamental frequency found are very close, we wind up with very similar numbers for the percent difference and percent error. This lab is now completed with another class. Here's some sample numbers for you to work with. They set the open tube length to 124 centimeters and determine the first resonating frequency is 128 Hertz. The tube is then closed and the length is set to 38 centimeters. The first resonance is heard at 221 Hertz. Complete the data tables. So here's our two data tables. Please take some time, fill them in, pause the video, and come back when you're ready to see the answers. Part 1 with the open tube is to calculate the speed of sound. Here's our equation. Velocity is 2 times the length of the tube times the frequency that was heard, where the first loudest sound was, that's your first resonating frequency, divided by n, which is equal to 1. We substitute in our values and we get 317.4 meters per second. Trial 2, the closed tube. We have this formula, and we have our speed of sound that we found in part 1. Here's the length of our tube, and we calculate that the first resonating frequency should be at 208.8 Hertz. Now, the students heard the first resonance at 221 Hertz. Calculate the percent error and percent difference in the fundamental frequency of the closed tube. Calculate the percent error and percent difference. For the percent error, we're using the frequency that was heard to be the resonant frequency over here. So it's 208.8 minus 221 divided by 221. We get a percent error of 5.52%. For the percent difference, where we acknowledge that neither value is generally accepted, we use this formula, and we come up with 5.68% difference. Since there is no simple way to determine the speed of sound in your lab, we can make a general comparison. The value of 317 meters per second calculated seems rather low. This might lead you to believe that the frequency generator is not producing the correct frequencies. However, the difference between the calculated first resonant frequency and the demonstrated first resonant frequency only show a small difference, so our data at least is self-consistent. You might discuss with your students that if you had some sort of volume meter telling you how loud the sound is, your results would be more accurate than relying on what you hear. Conclusion. In this lab, the speed of sound in air was calculated using a resonance tube, an open tube. In addition, the first resonating frequency of a closed and open tube were found. With this lab, the properties of frequency in open and closed tubes was observed. If time permits, you could also show students that the second resonating frequency for an open tube is found at approximately twice the first resonating frequency. Now you're performing the sound wave demonstration on your own. The necessary equipment, sliding sound resonating tube, sine wave generator, and the speaker is all assembled, but there is a problem. The frequency generator can only make sounds of 100 Hertz. Describe how you would adjust the equipment so you can measure the speed of sound with an open tube. Calculate the predicted value of the tube length for the fundamental frequency using the known speed of sound. So that's going to be L is n times the velocity of sound over 2f. Put in the numbers, and here's our generator that's limited to 100 Hertz. We get about 1.7 meters. Adjust the length of the tube from about 1.5 meters to 2 meters, which brackets the predicted value, looking for the length that gives you the loudest resonance. With the length and the frequency, we can now find the speed of sound with this equation. V is equal to 2LF over N.